Today you're going to start learning calculus. Calculus is basically the study of several types of problems. The first thing in calculus that we'll talk about are limits, and then you move into slopes of tangent lines, and then you talk about area under a curve. And all of those are three very important concepts in calculus. In this unit of study, or in this course of study, I'm going to be following the AP curriculum guide for calculus. Now, that doesn't mean that you can't follow these lessons that I have in this order. If, let's say, you're taking it in college or you're taking a course that's not an AP course, it's okay. You can still follow these. The basic principles in all of these courses are pretty much the same. You might have some topics that go a little bit on a tangent based, like, business math or business calculus, things like that I don't have to cover in the AP calculus course. So there are other little avenues that you can take that maybe I don't cover, but the basics of calculus is going to be the same universally no matter what course you're taking. I'm following the AP calculus curriculum. So basically calculus, and this section is an introduction to calculus, where I'm just going to give you an overview of the different things that we will learn throughout the year. Calculus is basically the math of limits, and you probably had some limits when you did pre-calculus. Limits are a kind of a layman definition. The limit is the y value that a function is approaching as the x value approaches a particular number from both sides. Now that thing here, from both sides, is extremely important, because a function can only have a limit at a specific x value, or sometimes it'll be called your c value, if that y value is approaching the same thing from the right and the left. If it's approaching different things from the right and left, it would not be considered a limit. You might have a partial limit, or a left limit, or a right limit, but you won't have a limit per se of the entire function at that point. It's possible to not have a limit at one point, but have limits other places on the functions. That's very common. So when we're talking about a limit, we're going to be talking about a specific x value and what's happening to the y value at that very specific x value. If it's approaching the same thing, then you will have a limit. In other words, if it's approaching the same thing from the left and right, you will have a limit. If it's not, you will not have a limit. You would have one-sided limits in that case. The second basic topic that you will learn in calculus is the slope of a tangent line. And basically what that means is we will have a function, and this is my function, f of x, and I have picked 2 points on f of x, a and b, okay? And the point A is the ordered pair x, f of x, because remember, the y value in any ordered pair is what we get when we plug the x value into our function f of x. So that would give us the ordered pair A. And then we have to consider the change in x here. Now in calculus, when we're talking about the change in x, that is said to be delta x. This little triangle here is a delta, okay? So the change in the x value is delta x. So what that means is, if this is x, and going from x to the next point is delta x, then this x value right here would be x plus delta x, if you just think about math theory a little bit there. And so the ordered pair B would be the ordered pair x plus delta x, comma, f of x plus delta x, to plug in to get the y value of the f of x function. We have to plug the x value into the f of x function, okay? So the ordered pair B would be x plus delta x, comma, f of x plus delta x. Now, it's not a big deal if you don't understand that yet. We'll get there, but hopefully you understand function notation well enough to understand that the y value is what you get when you plug the x value of that ordered pair in. The basic principle for the slope of a tangent line is, if we have 2 points and I draw a secant line between those 2 points. If we want to find the slope of a tangent line at a specific x value on our function, well then that's going to be the limit of the slope between your secant lines as your b value approaches your x value. And basically the principle here is that as we move this point B closer and closer and closer to point A, then the slopes between A and B are approaching the actual slope of whatever the slope is at A. Now you can kind of see that if you just kind of draw those secant lines. If I draw them all, look at what's happening to the steepness of the line there, okay? And this is called the slope of the tangent line. Now if you think back to your knowledge of geometry, what was a tangent line? Wasn't a tangent line the line that touches a curve at one exact point? Okay, so if you look at these slopes, the slope from this A to B is getting gradually less steep. You see that? As we approach, as our B value approaches the A value. And basically what we're seeing here is the slope of the secant line as B gets closer and closer and closer to A, or as B approaches A, is getting closer and closer and closer to the actual slope of the tangent line, okay? And this slope of the tangent line is what we will be doing when we are finding derivatives, okay? The third really famous problem in calculus is the area problem. And with the area problem, what we do is we're basically finding the area under a specific curve. So what I've got here are like this curve here. I'm going to name it f of x. And in the area problem, they're going to ask you to estimate the area under the curve using something called Riemann sums. And in Riemann sums, you could have a left Riemann sum, you could have a right Riemann sum, you could have a midpoint sum, or you could use a trapezoid rule to find the sum. And basically, all of those different problems are ways of estimating the area under the curve. And with your study of calculus and combining the area under the curve with a little bit of knowledge of limits, we see that as these rectangles get smaller and smaller, then the area under the curve is going to approach the actual area under our curve. And let me show you what I mean by this. To show you, I'm going to use left Riemann sums. And basically what I've done is I have taken points equidistant from each other so that I'm forming 4 different sections of the same width underneath my function. And then what I'm going to do is I'm going to draw it so that I've got a rectangle using the ordered pairs from my f of x value. I can estimate the area under this curve by drawing these rectangles. And what you'll notice here is I have this rectangle. I could take the area of this rectangle plus the area of this rectangle plus the area of this one plus the area of this one, and I could get an estimate for the area under that curve, but it's going to be a low estimate because I will be leaving out these little sections here. And what we find as we do this is if we make the width of these rectangles smaller and smaller, putting more and more rectangles in here, and then drawing our lines across, the area that we get when we add all those rectangles together gets closer and closer and closer, or approaches the actual area under that curve. So let me show you how that works. What if, instead of having 4 equal lengths, or 4 equal widths for my rectangle, I do twice that many. I do 8 of them. If I draw my straight lines, you see, I still have a little bit above each of these lines that I'm missing, but the amount of area that I'm not accounting for is getting smaller and smaller. And if you think about it, I could go and do this into 16ths. I could just keep doing this, making the number of rectangles that I'm putting this thing into a smaller and smaller width. And what you will see, and my lines aren't very straight, but what you will see is as I draw these little rectangles, the area, when I add all of these rectangles together, is going to get closer and closer and closer to the actual area under the curve. So the thought is, if I have an infinite number of rectangles here, then I'm going to get the exact area under my curve. And that is something called integration. And then as we continue with that pattern of integration, after we learn the basic principles of integration and the area under a curve, what we will do is we will start rotating that shape around a specific axis and find the volume of the 3D shape that will be formed. We'll find the volume of a 3D shape that maybe will be formed with some holes drilled in them. So there's a lot that we can do with the area problem as we move into our calculus knowledge a little bit further. In our first limit example, this problem says find the limit as x approaches 2 if f of x equals x minus 2 over x minus 2. Now, a lot of times when we do limits, first of all, let me show you this using limit notation. They want us to find the limit of the function f of x as x approaches 2. This right here and this notation right here basically mean the same thing. They can put the limit as x approaches 2 of f of x, or they could put the limit as x approaches 2 of x minus 2 over x minus 2. They could express that function either way. It really doesn't matter. But basically what they're asking us to do is they want us to figure out what's happening as x approaches 2 from the left and from the right. So we have to consider both sides. Now with limits, there is a shortcut you can use sometimes. It doesn't work in this one, but I want to show you that shortcut just to show you why it doesn't work. You could take what x is approaching and directly substitute that into the function to see what happens. If you get a nice real number answer, then you're okay. That is going to be your answer. But if you don't, sometimes you're going to get a form called an indeterminate form. And let me show you what that is. If I were to take 2 and directly substitute into the information there, if I plug 2 in for x, on the top I would have 0, and on the bottom I would have 0. Now, this is something called the indeterminate form. And you need to understand why it's the indeterminate form, okay? There are several different things we've learned about something like this. Several different rules that we've learned throughout the math courses that we've taken. We know that anytime you have 0 on the top of a fraction, that 0 divided by anything is 0, right? We learned that a long time ago. So like 0 over 1 is 0, 0 over 5 is 0, 0 over -8 is 0. We also learned that you cannot divide by 0. If you have 0 on the bottom, then the function, or this thing right here, is undefined. Well, we have 0 on the denominator. So which is it? Is the answer 0 here, or is the answer undefined? Another thing we've learned about fractions is if we have the same thing on the top and the bottom, then it equals 1. So we've got 3 different things that this thing, based on the math that we've learned already, could be. But none of those are right. Because all the rules work here, we can't tell which one is the actual answer. That's why we call this the indeterminate form. Okay, so the indeterminate form is when you have something like 0 over 0. Another situation for the indeterminate form, you could possibly get infinity over infinity for other things. Now this one is 0 over 0, but I could give you some examples where you will end up with infinity over infinity or negative infinity over negative infinity. Okay, so those would both be considered the indeterminate form because we can't tell what happens with that. So if we can't tell what happens when we plug in, we have to find another way to do this. Well, one way you could look at this and say, okay, if I look at this function, could it be simplified? Could I make it something simpler to maybe see what the answer would be? Well, and the answer in this case is yes. If you've got the same thing on top as you do on the bottom, then isn't that going to be 1? Okay, so looking at that thing, f of x is going to be equal to 1. But we still have a problem because this is our first time looking at a limit problem. We're not really sure what that means in terms of what we really have here. So I want to show you how to take this and graph it and determine what the answer is based on the graph. Because in this section, that's probably what we're going to do a little bit more than any of the other methods. So if I take this information and do a simple graph with it, I've drawn an XY chart here, and I'm just going to go maybe from 3 to -3 on all the axes and look at what's happening with our graph. Okay, so if I plug in 0, wouldn't I get -2 over -2? So at 0 we get 1 because -2 over -2 is 1. If I plug in -1, I would have -3 over -3, which is 1. In fact, this is going to happen for all of the whole numbers except for 2, and we'll talk about 2 in just a minute. So at -2 we have 1, at -3 we have 1. So it looks like this function, as we move that direction, all of the ordered pairs are going to be at 1. If we plug 1 in, we get -1 over -1, which is still 1. If we plug 2 in, this is the big thing here. Plugging 2 in is what gave us the indeterminate form. So there's no way for us to tell what that graph is doing at 2. But we do know that everything to the left of 2 is at 1. So what I'm going to do is just put a little hole in the graph leading up to 2. And then let's think about numbers to the right of 2. So if I plug in 3, I would have 1 over 1, which is 1. If I plug in 4, I would have 2 over 2, which is 1. And it looks like this pattern is going to continue to the right side of that hole as well. So basically what we have here is the graph of a horizontal line. Now, my graph's not real straight, but I drew it by hand. That's going to happen. So it's a horizontal line, but there's a hole at the x value of 2. Well, when we're talking about considering the limit, that doesn't matter because we just have to make sure that the limit is, as we approach x equals 2, we just have to make sure that that limit is the same on the left-hand side of 2 and the right-hand side of 2, or that that y value is the same as we approach 2 from the left and 2 from the right. So let's look at that. As our function approaches at the x value of 2, the y value of that function is going to be 1. As it approaches from the right-hand side, as that x value approaches 2, the y value still approaches 1. Since that limit is the same from the left and from the right, even there's a hole in the graph at that specific value we're approaching, we still have a limit there of 1. So in fact, when we canceled these two things out and got them to equal 1, that is the limit. And you'll find later in this chapter that that is one of our limit properties. When we have a function equal to a whole number like that, the graph is always going to look similar to this in some way. And as we approach that hole in the graph from both sides, the answer is in fact going to just be that whole number that we ended up with. So our limit here, the limit as x approaches 2 for f of x, is equal to 1. And the reason it's equal to 1 is because the function is approaching the same y value as we approach the x value of 2 from the left and as we approach the x value of 2 from the right. This is something called a piecewise function, and I want to make sure you remember how to graph piecewise functions because they do become quite common when we're dealing with limits. So first we're going to graph it, and then I'm going to give you a couple questions to think about based on what we end up with as your graph. Okay, so it says h of x equals x squared when x is not equal to 2, but h of x equals 1 when x equals 2. So basically what they've given us here is the point 2, 1 is on the graph, and everywhere else the function of x squared, y equals x squared, is also on the graph. So if you think about y equals x squared, well, that's your parent function for a parabola. So let's look at what that would look like first. So if we were just to graph h of x equals x squared, well, if you think about it, if x is 0, we would have y to be 0. If x was 1, well, y would be 1. If x was 2, y would be 4. Negative 1 would be 1, negative 2 would be 4, and so on. And we would get that basic parabola shape for our function on the top. Okay, but look at what the specifics of that piecewise function say. It says that this is our graph when x is not equal to 2. So that means at 2, something different is happening. So at 2, I'm going to need an open circle there because it tells us that this happens only when x is not equal to 2. So at 2, that is not the case. It's going to be a hole in the graph there. When you have a hole in the graph, your function is no longer continuous, okay? That hole in the graph makes us have a jump or a skip in the graph, and that's going to happen a lot. You should have learned in Algebra 2 and in pre-calculus that you're going to have asymptotes, you're going to have holes in your graph that are going to, kind of mess up continuity of your graph. So you have to understand how to deal with those continuity problems, okay? And then it does go on to say that h of x equals 1 when x equals 2. So basically, when x equals 2, h of x is going to be 1. That's just an ordered pair there. So the domain of this function is all real numbers because everything is accounted for. All of the x values are accounted for here or here, okay? But we do have an inconsistency in that graph there. And here's how they're going to ask you for limits, okay? They might say, find the limit as x approaches 2 for h of x. Well, that's asking us to approach the x value of 2 from the right and the left on the function that they gave us. So if I approach 2 from the left, they want to know, what is this function approaching? Well, that function as I approach from the left looks to me like it's approaching 4 from the left. From the right, as x approaches the 2, it also looks like it's approaching 4. So is it approaching the same thing from the left and from the right? Yes, it is. So the limit as x approaches 2 for h of x is 4. But what if they said, find h of 2? Now that's where this is different. H of 2 is the actual y value at 2? Well, at 2, the y value here is 1. So h of 2 is at 1. So this is one of our special cases where the limit as x approaches a number might be different than the function that you get, or the number that you get when you plug that x value into the actual function. So your limit does not have to be equal to what you get at that x value. They can be different, okay? The big thing here is you have to remember that your limit has to approach the same thing. The y value of the limit has to approach the same thing from the left and the right. In this one, they're asking us to find the limit of f of x when x approaches 3 if f of x equals x plus 2. Well, there are a couple different ways we could do this one. We could graph it and look and see what's happening at the left and the right. So let's do that. We learned in Algebra 1 that to graph a simple slope-intercept form function, the b value is 2, so that's where it crosses the y-axis. The slope here is 1, so from that point we can go up 1, right 1, up 1, right 1. We can continue that pattern, and here is our function. So that's f of x equals x plus 2. What's happening when x approaches 3? Well, at 3, if you look here, what is x approaching? Well, it looks to me like it's approaching 1, 2, 3, 4, 5, okay? From the right and from the left, your y value at x equals 3 is approaching 5. So the limit, I could write it in limit notation, as x approaches 3 for the function x plus 2 is 5. Now, let me point out, that is one of your most simple type of limit problems. If they were to just give you this, it really isn't necessary to graph that. You need to understand what that function would look like if you did graph it. But honestly, if you're going to do this and you're trying to use the most efficient way to solve a problem, because remember, if you're taking a lot of these tests, they're going to be timed, so we want to work most efficiently. Well, if I'm trying to determine the limit as x approaches 3, the quickest way to do that is to plug 3 in for x. If I plug 3 in for x, I get 5, okay? Now, sometimes you might plug that number in and get that 0 over 0, an indeterminate form, or you might get infinity over infinity, another indeterminate form, and then you'll have to do a little more math to get the answer. But in this case, if you can plug in and it gives you a nice answer that you can get, and you understand what it means and all that, that's how you want to do that limit problem. It makes it very, very simple. Okay, this is the last limit problem I'm going to do with you in this section. And this, basically, I've got a function f, and you can see function f dips down, comes back up, and we've got a hole in the graph. It looks like here at 3, okay? And it looks like at 3, the hole would be at maybe 2, very close to 2. So it says find the limit of f as x approaches 3. As x approaches 3 from the left, it appears that the y value is 2. As x approaches the x value of 3 from the right, it appears that the y value is also 2. So since these are approaching the same thing from both sides, the limit of f as x approaches 3 is going to be 2. Okay? So is that what f of 3 is equal to? No, because there's a hole in the graph at 3. If we were asked what f of 3 is, we would have to find the solid dot at 3. In this case, there isn't one. So we would have to say here, that does not exist because there's a hole in the graph. Does that happen sometimes? Yes, and we'll study that a little bit more in this chapter, but hopefully you remember from Algebra 2 and pre-calculus, when you were dealing with holes in graphs, you have holes in the graph when you have a common factor on the top and bottom that cancels out. So that's basically what's happened here. You had something, a factor, that canceled out. Okay, here are a couple problems. I want you to try these on your own. Go ahead and find the limit of f of x as x approaches 2 for the piecewise function f of x equals 1 when x is not equal to 2 and 0 when x equals 2. See if you can answer that question. And then for that same graph, I want you to find f of 2. Okay, so graph that on your own, and then we'll come back and compare answers in a few minutes. Go ahead and pause the video. So here I have the graph for this function. If f of x equals 1 for all values of x except 2, basically that's just the horizontal line at y equals 1. And then at x equals 2, we had a hole in the graph because at x equals 2, your f of x is equal to 0. So that's the ordered pair 2, 0. So this is the graph that they're talking about in part A. And if it says to find the limit of f of x as x approaches 2, well, we're looking from the left and the right as the x value approaches 2. Well, from the left, looks like the x value is approaching 1. And from the right, it looks like the x is approaching, or the y value of the x is approaching 1 as well. So the limit there is going to be 1. And then it says find f of 2. Well, f of 2 would be the solid dot when x equals 2. So the solid dot when x equals 2 is 0. So f of 2 is 0. So now it's important to start thinking about some limits that maybe don't exist. Okay, you need to understand when this happens. And so I'm going to show you a couple different examples of when this happens. Okay, in this one, we've got f of x equals the absolute value of x over x. And then they want us to find the limit as x approaches 0 for f of x. Well, if you think about this, now we talked about we could possibly just plug the x value in that the limit is approaching. Okay, well, if we plug that x value in, if we plug 0 in, look at what we end up with, 0 over 0. And we said earlier that that's our indeterminate form. So we can't tell what's happening at 0. So that suggests that at 0 it's undefined, or there's either an asymptote or a hole in the graph. Okay? So what we need to do is we need to consider what's happening for your x values when x is positive, and we need to consider what's happening when x is negative. Come up with a graph, and then look at that graph to see what's happening from the left and the right. Remember, the only time a function has a limit is if the y value is the same as x approaches a specific number from the left and the right. It has to be approaching the same y value in order for the limit to exist. Okay, so I'm just going to do this real quick. I'm going to make a real simple graph. I'll just go to 3. And again, we said we can't plug in 0, so we don't know what's happening at 0. Let's just try positive numbers first. Let's try positive 1. If I put 1 in here, I have the absolute value of 1 is 1 over 1, so that gives me 1. So at 1, we have a y value of 1. If I plug 2 in, absolute value of 2 is 2 over 2 is 1, so again, we get 1. And in fact, no matter what the positive number, you're going to get 1. Even if I plug in a half, 1/2 over 1/2 is still 1. If I plug in 1/4, 1/4 over 1/4 is still 1. Okay? So it looks like here for the positives, everything is going to approach 1. The only thing I don't know is what's happening at 0. So I'm going to put an open circle there at 0 because I don't know what's happening there. But we know to the right of 0, for all positive numbers, our y value is going to be 1. So now let's consider the left-hand side of the graph. If we plug in negative numbers, well, again, 0, we don't know what that is, but if I plug in -1, -1, the absolute value of -1 is 1, over -1 is -1. Let's plug in -3. Absolute value of -3 is 3, over -3 is -1 again. In fact, that same thing is going to happen no matter what negative value I put in. We're going to get -1. Again, the only place we don't know what's happening is at 0. So I'm going to have that as an open circle because we can't get the graph at 0. So here's my graph. So now, so when it has a jump in the graph like that, it's not continuous. Okay, well that's okay. And if we were to find the limit anywhere except for 0, we would be able to find a limit. For example, the limit as x approaches 3 is 1. The limit as x approaches 1 is 1. The limit as x approaches -2 is -1. So everywhere on this graph has a limit except at 0. Now look at what happens at 0. They're asking us here to find the limit as x approaches 0 for f of x. Well, if we approach from the left, it looks to me like it's approaching -1. If we approach from the right, it looks to me like it's approaching a y value of 1. Well, the y value approaching from the left is -1. The y value approaching from the right is 1. Those two y values are different. And remember, by definition, in order for the limit to exist, when your x value approaches the same thing from the left and the right, the y value it's approaching has to be the same from the left and from the right. If it's not, the limit does not exist. So in this case, at x equals 0, the limit does not exist because there's a jump in the graph there. We can't say it. Now, the left limit, the limit as x approaches 0 from the left would be -1. The limit as x approaches 0 from the right is going to be a +1. Those are called one-sided limits, but we'll talk about how that affects some of the math that we can do later. But for now, we're just approaching the same thing from the left and the right. If the y value is not the same, we have to put does not exist. And last, I want to consider what happens with this function, f of x equals 1 over x squared, and we want to find the limit as x approaches 0 of f of x. Again, I'm just going to do a real simple graph here. Now, if you consider this, we learned back in Algebra 2 that we have some vertical asymptotes. Anytime you have a 0 on the denominator, you have a vertical asymptote. So look at what happens when x equals 0. Don't we have a vertical asymptote at x equals 0? So that means my y-axis is actually an asymptote. So we know that my graph is going to approach that y-axis, but it probably won't cross it. Now, there's nothing that says an asymptote can't cross it, but I'm going to guess and say for this one it doesn't. And then I'm going to just plug in some other numbers, like let's plug in 1. If x is 1, I have 1 over 1 squared, which is 1. If x is 2, I have 1 over 4, so that's 1/4. If x is 3, I have 1/9. X is 4, 1/16. So it looks like to me, as I go to the right, it's approaching the x-axis. So that is approaching 0 here as it goes to the right. And then what's happening, we've got to consider, we know 0, we don't have any numbers, but we've got to consider what's happening between 0 and 1. I'm going to plug in 1/2. If I do that, I have 1 over 1/2 squared is 1/4. 1 over 1/4 is 4. So 1/2 would be 4. So it looks to me like this thing is getting really big really quickly. So it's approaching that y-axis. And then on the left, we could do some similar numbers. If I plug in -1, we would get 1. -2 would give me 1/4. So it looks like it's kind of doing the same thing on the left, just approaching 0 from the other direction. And then if I plug in again 1/2, I would get 4. So again, it's going up really quickly toward that y-axis. So this is what my basic graph looks like. Now, there's nothing to say you can't do that on your calculator. You could, and then look and see what's happening. But sometimes with the calculator, since they don't label the graphs very well, sometimes it's hard to tell what the graph is doing or where those numbers are. It just depends on what you're using. So graphing calculators are a little bit harder in calculus than maybe Desmos. But then if you're taking the AP Calculus test, I don't believe they let you use Desmos, so I wouldn't get in the habit of using that too much. It's good to know how to do this by hand. So then if we're doing this and we're looking for the limit as x approaches 0, well, in order for a function to have a limit, it has to approach the same thing from the left and from the right. Well, looking from the left, we don't know what it's approaching. It looks like it's approaching this line, but it looks to me like it's approaching infinity. And here, same thing. It looks to me like it's approaching infinity, okay? Well, some textbooks tell you that that's a does not exist because there's no definite number it's approaching. But since really they're both approaching infinity from the left, it is okay to say that it's approaching infinity, okay? I would also accept does not exist for where we are in the course at this point, okay? But later, your does not exist is going to turn into infinity anyway. So to me, if you want to go ahead and say infinity, I'm okay with that, okay? Depending on what book you're using, they might be sticklers for the does not exist at this point in the course, okay? It just depends on the writer or the author of the book. But infinity or does not exist would be okay, at least for now. Later, I'm going to say you have to put infinity. So we might as well do that now.